Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural analysis, drawing shear and moment diagrams without the use of equations. In this video we will learn about drawing shear and moment diagram without using any equations. How to draw them without using equation. Here we focus on how to construct the shear diagram directly from the load diagram, and how to construct the moment diagram from the shear diagram. Suppose we wish to construct shear and moment diagram for a simply supported beam subjected to a uniformly distributed load, UDL. Observe that the beam has two upward reaction, each having a magnitude of WL/2. Basic facts that enables us to draw the shear diagram directly from the load diagram is this: the change in shear in a beam segment is equal to the total load applied to the segment. Change in shear in a beam segment equals to the total load applied to the segment. So, if we know shear at A and we know much load is being applied to segment AB, then we can easily calculate shear at B. That is, shear at B is equal to shear at A plus total load applied to the segment. Shear at B equals shear at A plus total load at AB. Total load applied to the beam segment, here is the area of the rectangle having L as its base and W as its height. Therefore total load is negative WL. The negative sign indicate that the load is acting downward to draw the shear diagram. For the beam segment we need to have these following information. 1. Shear at the left end of the segment. 2. Shear at the right end of the segment. 3. The shape of the curve that connects the 2 points. In case of simply supported beam, shear at the left end of the beam always equal to the support reaction at the end. Since there is an upward reaction of WL/2 at the left end of the beam, then shear at that point is positive and WL/2. Shear at right end of the beam segment equals to the shear at the left end plus the area under the load diagram between the 2 points. Therefore, shear at the right end is WL/2 minus WL. Shear at B equals WL/2 minus WL equals minus WL/2. Now, we know the shear at either end of the segment. We need to draw the curve representing shear within the segment. Since here the load is constant throughout the beam segment, then we draw a straight line connecting the 2 points, that is, shear is linear in the beam. A beam segment subjected to a uniformly distributed load carries Allen-Early varying shear. Concerning the shape of the diagram, the underlying rule is this: if we view the load diagram and the shear diagram as polynomials, then the degree of the shear polynomials is 1 higher than that of the load polynomials. since the degree of the load polynomial in this example is 0. The load is constant, then shear polynomial has a degree of 1. Shear varies linearly in the beam. Note that the shear diagram consists of a positive region and a negative region, where shear being 0 at the midpoint of the beam. Let us label positive region R1 and negative region R2. Now, we draw the moment diagram using the constructed shear diagram. To do so, we need to calculate the area under the shear diagram. Since the diagram consists of two regions, we need to calculate two areas. Positive area associated with R1, positive area. Negative area associated with R2, negative area. R1 FORMs a right-angled triangle with a height of WL/2 and base of L/2. Therefore, area is W times L times L, /8 as area of triangle is equals 1/2, times B times H. R2 has an area equal to W times L times L, /8, but this area is negative, since the region is below the x-axis. The diagram represents the areas of R1A and R2. Now, we draw the moment diagram segment by segment. It's as usual to do from left to right, so first we draw the moment diagram for R1, then we do it for R2. To draw moment diagram for R1, we start from left end of the beam, we examine the reaction at that end. Since there is no moment reaction there, then moment at the left end of the segment is 0. Moment at the right end of the segment equals to the moment at the left end plus the area under the shear diagram in the segment. That is, moment at the right end of R1 equal to 0 plus W times L times L/8. Moment at midspan equals. Now, we have moment value at the ends of the segment. Now connecting them using a curve, indicating how moment changes within the segment. Similar to the curve representing the shear diagram, the moment diagram curve is polynomials. The degree of this polynomial is 1 higher than that of shear polynomials in this example. Since the shear diagram is linear, the shear polynomials has a degree of 1. Then the moment diagram needs to be drawn using a polynomials of degree 2. A curve representing quadratic equations. But such a curve can be drawn in two ways. Either decreasing slope or increasing slope. See figure below. As we see the figure, the first curve that has decreasing slope. The slope of the curve decreases as we move from left to right. Similarly, in the second curve it has an increasing slope, its slope increases from left to right. So, which one is the correct curve? Does the moment in the segment of the beam have an increasing slope or a decreasing slope? For this, to answer the question, we need to examine the shear diagram. If shear in the segment is increasing in value, then the slope of the moment curve should increases. If shear is decreasing, moment should also have a decreasing slope. Shear in region R1 is positive. See figure, but decreasing in value from left to right, that is, the shear value of the left end of the segment is higher than the shear value at the right end of the segment. Shear at the left end of the segment is WL/2, whereas shear at right end is 0. Therefore, the moment curve needs to have a decreasing slope. So the correct diagram for the left segment is. Similarly, for the right segment of the beam. At the left end of the beam, moment R2 is the same as the moment at the right end of R1. Therefore, we start with moment value of positive W times L/8. Moment at the right end of R2 equal to the moment at the left end of the segment plus the shear diagram in the segment. Since the area is negative, then the right moment is 0. Moment at B equals W times L/8 minus W times L/8 equals 0. Just like before, there are two options for connecting the 2 points: a curve with decreasing slope, or with an increasing slope. To decide the correct shape for the diagram, examine the shear diagram of the segment. Does shear diagram have an increasing value or decreasing value? In our case, shear goes from 0 at the left end of segment and negative WL/2 at the right end of the segment, that is, shear decreasing in value from 0 to negative WL/2. Therefore, the slope of moment diagram is decreasing slope. Slope changes from 0 at the left end to a very large, negative value at right end. Therefore, the moment diagram for the entire beam looks like as seen in the figure below. Example 2. A simply supported beam subjected to two concentrated loads. First, we will calculate support reaction. Reaction at A plus reaction at B equals 10 plus 4. Equation number 1, taking moment about B. Reaction at A times 8 equals 4 times 2 plus 10 times 4. Reaction at A times 8 equals 8 plus 10. Reaction at A equals 48/8 equals 6 kilonewton. Reaction at B equals 8 kilonewton, from equation number 1. Left reaction is 6 kilonewton and the right reaction is 8 kilonewton. Concentrated loads divided the beam into 3 segments into A, B, C, C, D. We are going to construct the shear diagram segment by segment. For segment AB, because there is an upward reaction of 6 kilonewton at the left end of the segment, shear at that point is 6 kilonewton. The area under the load diagram in this segment is 0. There is no distribution load applied to the segment. Therefore, the shear at the right end of the segment is 6 kN. Shear at BIS equal to 6 kN. That is, shear at right end equals to the shear at the left end plus area under the load diagram within the segment. Therefore, shear in the segment remains constant with a magnitude of 6 kN at point B, since there is a downward force of 10 kN. There is going to be drop of 10 units in shear value. So, shear is going to drop from +6 at the immediate left to BTO -4, at the immediate right of B. Shear at B equals 6, minus 10 equals, minus 4. Therefore, the shear at the left end of the segment BC is -4. Since there is no load applied within segment BC, the total load applied to the segment is 0. Hence, shear at right end of the segment is -4. Shear at C equals, minus 4 plus 0 equals, minus 4. Similar to segment A, bin segment B, shear remains constant. Shear just to the left of point C is -4. Given that there is a downward force of 4 kN at C, then shear just to the right of the -8 kN. Shear at C equals 8 kN. That there is a drop of 4 in shear value, right at point C. Similar to the other two segments, total load applied within segment CD is 0. Therefore, shear remains constant throughout the segment. Shear remains -8 kN in segment CD. To draw the moment diagram, let us start calculating the area under the shear diagram. In each segment, for segment A, BIS plus 24. Area of AB equals 4 times 6 equals 24. Area of BC equals 2 times, minus 4 equals, minus 8. Area of CD equals 2 times, minus 8 equals, minus 16. For segment AB, moment at the left end of the segment is 0. Since there is no moment at the pin support at A, then the normal at the pin support at A, then the moment at the right end segment is 0 plus 24. Moment at A equals 0. Moment at B equals 0 plus 24 equals 24 kN-meter. Since shear is constant in the segment, moment is linear. Why? If we view shear and moment graphs as polynomials, the degree of moment polynomials should be 1 higher than that of the shear polynomials. Shear is a polynomial of degree 0. Since shear does not change within the segment, therefore moment has to be represented as a polynomial of degree 1, which is the equation for a line, so moment varies linearly in the segment. For segment BC, we know the moment at the left end of the segment, it is same as the moment at the right end of the previous segment. So, moment at the end of the segment BC is positive 24. For moment at the right end of segment BC is 24, minus 8 equals. Moment at B equals 24 kNm. kilonewton meter. Moment at C equals 24, minus 8 equals 16 kNm, kilonewton meter. Similarly, to previous segment, moment in segment B varies linearly, as in the figure. Finally, for segment C, the following same pattern we used for other segment. Moment at D equals 16, minus 16 equals 0. So complete diagram of the shear force and bending moment is as shown in figure. Point to remember for drawing. Shear moment and bending moment diagram. For cantilever beam. First, draw reference line. Positive value upward the reference line. Negative value draw downward the reference axis. Shear force diagram may be negative or positive or both. Bending moment diagram is always negative. When point load is applied, the shear force diagram is horizontal and vertical straight line. When uniformly distributed load is applied, the shear force diagram is inclined straight line. When uniformly varying load is applied, the shear force diagram is horizontal and vertical inclined line. When point load is applied, the bending moment diagram is inclined straight line. When uniformly distributed load is applied, then bending moment diagram is parabolic. When uniformly varying load is applied, the bending moment diagram is cubic parabola. For simply supported beam. First, draw reference line. Positive value upward the reference line. Negative value draw downward the reference axis. Shear force diagram may be negative or positive. Bending moment diagram is always positive. When point load is applied, the shear force diagram is horizontal and vertical straight line. When uniformly distributed load is applied, the shear force diagram is inclined straight line. When uniformly varying load is applied, the shear force diagram is horizontal and vertical inclined line. When point load is applied, the bending moment diagram is inclined straight line. When uniformly distributed load is applied, then bending moment diagram is parabolic. When uniformly varying load is applied, the bending moment diagram is cubic parabola. For overhanging beam. First, draw reference line. Positive value upward the reference line. Negative value draw downward the reference axis. Shear force diagram may be negative or positive. Bending moment diagram is positive or negative. When point load is applied, the shear force diagram is horizontal and vertical straight line. When uniformly distributed load is applied, the shear force diagram is inclined straight line. When uniformly varying load is applied, the shear force diagram is horizontal and vertical inclined line. When point load is applied, the bending moment diagram is inclined straight line. When uniformly distributed load is applied, then bending moment diagram is parabolic. When uniformly varying load is applied, the bending moment diagram is cubic parabola. Thank you for watching.
Thank you for watching. Please subscribe to the channel and press the bell icon.